Hello, this is video 37, the last video for this unit, and I just want to talk about one more of Newton's laws, which is called the law of universal gravitation. So, it's a lot of words here, but basically all it says is that whenever you have two masses, they're going to attract each other. And the amount by which they attract each other depends on how massive they are. The more massive, the more they're going to attract each other, and how far apart they are, which is r, the distance between the centers of the two objects. So we have the equation right here, F sub g equals g m1 m2 over r squared. So you can see from the equation that the force depends directly on the masses because they're on the numerator, and the force depends inversely on the square of the distance. So when something depends inversely on something, that means that if you increase the distance, because it's in the denominator, then the force is going to decrease. As the objects are further away, they're going to feel less of this gravitational force. G, the big capital G, is a constant of universal gravitation. So this constant doesn't change. It's not the same thing as little g. We'll see that later in this video. So this G doesn't change. So this force is always attractive. Objects never repel each other due to their masses. So let's take a look at a couple of questions. So example 6, you're seated in your physics class next to another student 0.6 meters away. Estimate the magnitude of the gravitational force between you. Assume that you each have a mass of 65 kilograms. So this is just a plug and chug problem where you're finding that gravitational force between the two objects. So the masses, and I'll just plug them in because this is just plug and chug. So we're going to plug in the G, which is 6.67 times 10 to the negative 11, the M1, which is 65 kilograms, and the M2, which is also 65 kilograms. And then we're going to divide by r squared, the distance between the two objects. It's supposed to be between the centers, but this is the best distance that we have, so 0.6 squared. Plug it into your calculator, and we're going to get 7.83 times 10 to the negative 7 newtons. So the point of this plug and chug problem is that this gravitational force is extremely small when you're talking about two human beings. That's why when you're sitting next to somebody, you don't feel attracted to them, all right? Even though you may be secretly attracted to them, you don't feel physically pulled in toward them. So let's take a look at a couple more questions. If the distance to the moon were doubled, then the force of attraction between Earth and the moon, how would it be affected? So the moon and the Earth are two objects that have mass, so any two objects that have mass feel this gravitational force between them. So the form of the equation is gmm over r squared. So this is talking about what happens when you change the distance. So we are doubling the distance, we're making the distance bigger. So without worrying too much about the r squared here, just because of the fact that it's doubled, that will limit your answer choices. We said the bigger the distance, the less the force. So we can already eliminate choices A, B, and C. The bigger the distance, the less the force, so we can eliminate choices C, D, and E, because there the force is staying the same or getting bigger. So how much smaller does the force get when the objects are further apart? Instead of being this far apart, they're this far apart. The distance has doubled. Well, the best way to do this is to plug in here for r, to plug in 2r, but make sure that you square it. So you're going to say, well, the new force here is going to be gmm, but now you have 2r, right? This was r here, this is 2r. And you have to square that, and look at what happens. You get 4r squared. So the original force with r was gmm over r squared, and with 2r, it's 1 over 4 times gmm over r squared. So the force is 1/4. So this pops up a lot. If something is squared and you're doubling it, then the result is going to be changed by a factor of 4. And we also like to say that Newton's law of gravity is an inverse square law because of the dependence of the force on this radius squared. Let's take a look at one more your turn here. The force of planet Y on planet X is blank the magnitude of the force of planet X on planet Y. So we see planet X has twice the mass as planet Y. So the two will be attracted to each other. How do the forces compare? Well, this actually goes back to Newton's third law. Newton's third law says if one object pulls on the other, then the other pulls on that one with the same exact force, but in the opposite direction. So the answer is that it's the same force. So don't be fooled by the fact that one is more massive than the other. All this means is that let's say you had two objects that were less massive, well, they would both be pulled with a smaller force. If one of the objects is more massive, then each of them feel a greater force, but that force is the same for both of those objects. So let's finish up this section here. I have one more thing to talk about. So now we can talk about little g. Why have we been using g as 9.8 when we're on the surface of the Earth? So the reason being is because when we're on the surface of the Earth, so I'll draw us as a little ball here, and this is definitely not to scale, we have said that we have our weight pulling us down. Well, our weight pulling us down is really the Earth pulling us down. It's really the gravitational force of the Earth acting on us. So our weight that we feel is the same as the gravitational force from the Earth. So we can set the two forces equal to each other. mg equals gm m sub e over r sub e squared, where m of e is the mass of the Earth and r sub e is the radius of the Earth. And we don't care about the radius of the person because the person is so small compared to the Earth. So r sub e, the radius of the Earth, really is the distance between the little mass and the big mass, because that distance has to be between the centers of the two objects. So now when you cancel out the little m, then you're left with g. You plug in the mass of the Earth and the radius of the Earth squared and multiply it by g, the universal gravitational constant, you will get 9.8 meters per second squared. So that's why we have been using this. But we have mentioned that if we go on Mars or on the moon, that little g here is different. That's because we have to substitute in the mass of Mars and the radius of Mars, and we're going to get a different value for little g. One last thing that I'd like to mention about this gravitational force, to kind of recap, is it's really insignificant when you're talking about small masses like 2 students, but once you have at least one massive object such as the Earth or Moon, then this force becomes very significant, right? This gravitational force is responsible for your weight pulling you down. If you have the Earth and the Moon, the gravitational force between them is responsible for the Moon going around the Earth. So it's very significant when the masses are big, but when the masses are small, that gravitational constant just makes that force much too small for it to be noticeable. If we look back at that original slide, that gravitational constant is such a small number that the masses need to be big to overcome this small constants.